These are the neutralization notes. It'll be helpful to have a calculator to use throughout these notes. Acid-base reactions are neutralization reactions. So when those acids and bases react, the products most commonly formed are a salt, which is an ionic compound, and water. This is called a neutralization reaction. Remember, if something is neutral, it means it has either both that H and that OH, like water, or it has neither of those. And so any of our ionic compounds or salts fall into that category. And so with that, our products of an acid-base reaction are neutral. And so as we are looking at determining if something is neutral or not, we need to look at, well, how many hydrogens do I have compared with how many hydroxides do I have? And then those pair up. If I have those where each hydrogen is going to have an OH, then all of those will get used up and we'll end up with only neutral products. But if, let's say, I have more hydrogens than I have hydroxides, then I might have some excess H plus hydrogens, resulting in an overall acidic solution after that reaction. And vice versa, if we have more hydroxides than hydrogens, we might have an excess of those OH ions, resulting in a solution that is more basic with that. And so that's what we're going to look at today, is if I have an acid and a base producing salt and water, so a neutral outcome, we're going to look at, well, how much of our hydrogen ions do we have, how many hydroxide ions do we have, and comparing those to determine, was neutralization our result? If not, is our resulting solution acidic or basic? So some applications of neutralization reactions. They are involved in a lot of medications known as antacids, which are used to relieve heartburn by neutralizing that excess stomach acid. So magnesium hydroxide is a common ingredient in antacids because it reacts with the hydrochloric acid in the stomach. And so in order to neutralize that, you have that basic magnesium hydroxide that you're consuming, and then that is reacting with that hydrochloric acid, and then you would hopefully produce neutral products, decreasing that heartburn. So when we are considering neutralization, neutralization is achieved when we have a strong acid and a strong base that are combined so that however many moles of hydrogen ions we have is going to equal the moles of hydroxides. And again, thinking of that neutralization reaction, that means that every H is going to have an OH to pair with. And so then that would also mean that what they're leaving, those also have pairs. So we're not actually left with any excess base or excess acid in a neutralization reaction. And so our strong acids completely dissociate. So again, whatever our moles of acid are going to be our moles of hydroxide. Our strong bases completely dissociate all of their OHs. And so we do need to check our mole ratio or the number of moles of hydroxide we have in that compound. We could do this with weak acids and weak bases. We are only going to look at doing this type of neutralization problem with strong acids and bases for our purposes, just of not making each individual problem too complicated. So we are going to focus on strong acids and bases in looking at, is our resulting solution neutralized? After mixing together an aqueous solution of a strong acid with a strong base, the resultant solution could be neutral. So if we get that our moles of hydrogen ions is equal to our moles of hydroxide, then we're going to get complete neutralization. If we have more hydroxides than, more hydrogen ions than hydroxides, that means we're going to have those excess H+, and so that would be a resulting acidic solution. And then if we have more of those hydroxide ions than our hydrogen ions, that would result in a basic solution. Since we are most often given concentrations and volumes, we are going to use that molarity equals moles over liters in order to look at calculating those moles. And so when we rearrange that, we get that moles is molarity times liters, or if you like using the kind of triangle approach, moles is going to be that molarity times liters here. This molarity formula is on your pink sheet for you to access and reference. You can always draw this triangle as needed if that is helpful to you. So just kind of a visual looking over this. Our acid, base, and neutral. So if we have more of, and again, this H3O plus is the equivalent to our H plus, it just has the water in it. But if we have more of those H plus, that is going to be a resulting acidic solution. If our concentrations are the same, that's going to be a neutral solution. And if we have more of those OH ions, that is going to be a resulting basic solution. So we're going to have to find these values and compare in order to determine what is our resulting solution going to be, and then to determine what is the pH or the pOH of that resulting solution. So here are the steps kind of written out. We're going to go through these in an example. The first thing is that we need to find the moles of our acid and the moles of our base using that rearranging of our molarity formula. So we're always finding those moles first. And then we're going to look at comparing those. What do we have more of? And that whatever that excess is going to tell us, is it acidic or basic based on what we have that excess of. We're going to actually calculate how much excess we have. And then we can use that to find, well, what is the concentration of those excess based on our value we have for moles of excess and liters of our full solution. And once we have that, it's going to tell us our H plus or our OH, depending on what that excess is. All right, so let's go through an example. This has the steps for us. You are going to need to know the steps on your own, but this is going to walk us through it. So we have 42 milliliters of 0.37 molar hydrochloric acid is combined with 35 milliliters of 0.25 molar NaOH. Determine the results of this reaction. And so kind of our goal results being, is this acidic? Is this basic? Is this neutral? And depending on what those are, we're going to then be able to figure out the pH, pOH, H plus concentration, and OH concentration for it. All right, so first step is finding moles of each. And do note that we have only strong acids here. Hydrochloric acid has a Ka of greater than 1, and then NaOH is one of our strong bases. So finding moles of each, so I've got my 42 milliliters of 0.37 molar HCl. Well, finding my moles of HCl, moles of anything, is molarity times liters. Again, I'm rearranging that molarity is moles over liters, getting moles by itself, so that molarity times liters is our first step. We do need liters though, so moving my decimal, 1, 2, 3, my moles of HCl is my molarity 0.37 molar times liters, 0.042 liters with that. I'm dropping the zeros at the end. I'll take those into consideration in my sig figs in a minute. But because this is 2 sig figs, keeping those zeros on the end isn't going to make more sig figs with that. All right, so then we get 1.6 times 10 to the negative 2 moles, and that is of our H plus ions, because that would be however many moles we have of our HCl, but we know that these are all going to break off 1, and so that is our moles of HCl, but then that also is our moles of H plus. Now, as we look at our base, 35 milliliters of 0.25 molar NaOH. I'm going to find my moles of that NaOH. I again need, move that decimal, 1, 2, 3, I need liters. So moles of my NaOH is going to be molarity 0.25 molar times 0.035 liters. Again, if I'm dropping these zeros, even though they are significant, because this does just have 2 sig figs. And then I get 8.8 times 10 to the negative 3 moles, and that's my moles of NaOH, but I only have 1 hydroxide, so that is also my moles of my hydroxide ions. And so now we're looking at comparing. Which one do we have more of? Because these are not the same value. This one is 10 to the, and this is supposed to be a negative 2. I think my negative just is not visible. So 10 to the negative 2, 10 to the negative 3, we are looking at which one do we have more of and how much. And so negative 2, that is a larger number. And so we have excess of the H plus ions from that acid. So this is going to be an acidic resulting solution. Let's find then how much we have excess of. So we have excess H plus. We're going to use up all of these OHs by pairing them with an H plus, but then whatever is left over is going to result to that solution being acidic. And so calculating excess, we're going to take our larger number minus our smaller number. And so those excess H pluses, I'm going to do 1.6 times 10 to the negative 2. And this is again moles minus 8.8 times 10 to the negative 3 moles. And when we do that subtraction, I get 7.2 times 10 to the negative 3, and that's going to be moles of H plus, because we took those moles of H plus minus the moles of OH, and so this is my excess hydrogen ions, which is what's contributing to this being an acidic solution. So we determined what we have more of. Well, if I have this many excess H plus ions, then this is going to, those moles, I can now find, well, what is the concentration of those H plus ions? And so we found 2, so now in step 3, let's actually find what is the concentration. We don't want how many H pluses do we have, but again, concentration, molarity is moles over liters. We know that we have those excess H plus ions as our moles over, we need the volume of this whole solution. And so as I look at this, I have 2 solutions that are getting put together. I have those 42 milliliters and the 35. So when I add those together and combine those, I need that total volume. And so we're going to have that 0.042 liters plus that 0.035 liters. That total volume is going to need to be in the denominator as we find what is the concentration of our H plus ions. So either putting parentheses here or adding those before you do your division. So we take our excess divided by the total volume, and that is moles divided by liters. And so that is going to be 0.094. I didn't do a very good job of talking about sig figs. 2 sig figs, 2 sig figs. So when we subtracted, 1 digit after the decimal. So that 1 digit after the decimal. And then when we're dividing 2 sig figs here, and then these ones, when we add them together, end up with 2 sig figs. So I've got those 2 sig figs. And that is my concentration of H plus ions in the solution. And now I found that first of my values. And now from there, once we have that H plus, we are able to do those steps that we have normally done with our other formulas. So looking at our formula sheet now, we have those H plus ions. Well, I can find my pH based on that concentration. And so even though step 4 has that OH, I'm going to actually find my pH next, because pH, as I look at my formula sheet, is negative log of my H plus, so negative log of 0.094. When I plug that into my calculator and I get that out, I'm going to have 1.03 as my pH, and 2 sig figs mean I need 2 digits after the decimal. So this is 2 sig figs. Normal sig figs for concentrations, but for pHs and POHs, we do digits after the decimal. So 1.03, that makes sense because this is an acid. We should have a low pH. What can I find next? Well, next I can do that POH, because I know that pH plus POH is equal to 14, and that's on our formula sheet. So to find that POH, 14 minus 1.03, keeping those 2 digits after the decimal, 12.97. And again, this is 2 sig figs, 2 digits after the decimal. And then that last step is going to be being able to find the OH concentration. So finding that OH concentration, well, that's 10 to the negative POH. And so we will have 10 to the negative 12.97. 2 sig figs there. And so plugging that back in, we get 1.1 back to regular sig figs, because this is a concentration, times 10 to the negative 3 molar. And that's the last piece of our information that we needed. So once you are able to find that H plus concentration, then we are able to start and go through our other formulas like we have in the past. But it is these steps of finding how many moles of each do I have. And then what we're doing is visually looking at what do I have more of and how much do I have more of. So finding that excess and then using that excess to determine what is the concentration for the entire solution. So molarity is moles over liters of the entire solution with that. All right. So if you want, go ahead and try example 2 on your own. Otherwise, you can go through it with me. So we have 26 milliliters of 0.15 molar HBr is combined with 48 milliliters of 0.12 molar BaOH2. Those are both strong. So determine the results of this reaction. So again, we're thinking, is this going to be acidic, basic, or if they have the same number of moles, is it going to be completely neutral? With this, I sometimes will look at these and say, okay, this is a solution. Our first solution is that HBr solution. And so when we look at this, we have 26 milliliters or 0.026 liters of this 0.15 molar solution. I am then going to combine that with my BaOH2 solution. And again, we have 0.048 liters of 0.12 molar solution. Those are getting combined. And so then in our results, I like to think about the fact that this mixture is going to have that 0.026 liters plus that 0.048 liters, like that. And now we want to look at, okay, are my hydroxides, are those neutralizing all my hydrogens, or am I going to have something excess with that? And so in order to do that, we need to find the moles of each. So doing that picture is not necessary, but if that kind of helps you think of what's happening, now we want to figure out when those go together, do we have excess of one of those? So finding our moles of each, I'm going to start with my moles of my acid, HBr. Well, moles is molarity times liters. So we're going to have that molarity, 0.15 molar. times 0.026 liters. I dropped my zeros just because I can see I'm going to have 2 sig figs after this. And when I do that, I get 3.9 times 10 to the negative third. That is how many moles of HBr we have. But because this is going to completely disassociate, that is also how many moles of hydrogen ions I'm going to have that I'm contributing. So now let's look at our barium hydroxide. Let's find how many moles of barium hydroxide are we contributing. Molarity times liters. That molarity is 0.12 molar times liters, 0.048. And I get 5.76 times 10 to the negative 3. And that is our moles of barium hydroxide. But with our bases, we have 2 moles of OH that are going to break off for every mole of our compound. And so we do need to take that 2 into account and multiply this by 2 in order to figure out our moles of hydroxide. And so when I multiply that by 2, I get 0.01152 or 1.152 times 10 to the negative 2, which with 2 sig figs would be 1.2 times 10 to the negative 2. That's how many moles of OH ions we have. And now that's what I need to compare to my moles of H+. And so as we look at these, now that I'm done with my multiplying, I can do sig figs at this step because the next thing I'm going to have to do would be subtraction of some sort. And if this since this has a higher exponent, that means that we have excess, we have more OHs, meaning this is going to result as a basic solution. And so we figured out how much, which we have more of, so we have more OH ions. And so now let's look at how much excess do we actually have. We know that we have more OHs, so let's go ahead and actually find the value of how much. And that is going to be looking at our step 2. All right, so in that step 2, we're going to take our larger number minus our smaller number. So to find the excess, your larger number is 1.2 times 10 to the negative 2. That's our moles of OH. And then we are going to subtract off our 3.9 times 10 to the negative 3. Those are our moles of H+. If you accidentally put the wrong one first, you'll just get a negative number and just make it positive. And then that just means you identified your excess wrong. So if you put your H pluses first, you would get a negative, and then you'll know that the OH is actually excess if you put your H pluses first and you get a negative difference. Okay, so we have now, though, we can do that subtraction. 2 sig figs, but with subtraction, we're looking at digits after the decimal. And so when we subtract those, I get 8.1 times 10 to the negative 3 moles of OH, and that is the excess moles of OH. And so I've got 8.1 times 10 to the negative 3 moles of unpaired OHs. The rest of the OHs paired up with all of our hydrogen ions. And so now we can find, well, this is OH concentration. Let's find that OH concentration by doing moles of excess divided by our volume of solution. So we've got that 8.1 times 10 to the negative 3 moles of our OHs all over volume of our solution. Remember, we put both of these together, and so now I need to look at, well, what is the sum of those volumes? I have that total volume, and that's what I'm going to put down here. And if you want, you can go ahead and add them first, or you can just write them out like this. And those are measured in liters. And so making sure that either you are using your E button here, using parentheses to add these, or just add them and then do your division. We end up with an OH concentration of 0.11. I'm going to those 2 sig figs again. And that is molarity. That is our concentration of our OH that is excess. So I've got that 0.11 molar. Then I'm able to go through, I have that. I need to then find my POH. So step 5 would be to find that POH. We know that POH is the negative log of our OH concentration. So negative log of that 0.11. And we get 0.96, 2 sig figs, those 2 digits after the decimal. We can then find our pH. That pH is going to be 14 minus our POH, 0.96. So we would have a pH of 13.04. And it makes sense that this is a high pH because we have a basic solution as our outcome. And then after we have that pH, we can find kind of our last calculation is, I think I might have missed number 4, 5, 6, 7. That's fine. Our last calculation is our H plus. So 10 to the power of that negative 13.04. 2 sig figs, we have 9.1, back to regular sig fig rules for a concentration, times 10 to the negative 14. And then that would be molar, so we need those units on the end. All right, so this is the same as, because we're dealing with these strong acids and bases, once we have the excess and we can find that excess concentration of whatever, or the concentration of whatever we have excess of, we're just following those formulas through. And these pH formulas are all provided on your formula sheet. All right, I worked out example 3 ahead of time. Feel free to give it a try on your own so that you can take a look. This one does end up having an excess of OH again. And so then we do start with finding that OH concentration, following our similar steps to before. There is a worksheet for practice. Reach out to your teacher with any questions.